Assalamu alaikum students. Our today's topic is bisection method, which is also called Bolzano method or interval halving method. It was introduced in 1817 by Bernard Bolzano. It is also called as Bisecting method. The method is guaranteed to converge for a continuous function on the interval. Basically, it's a root finding method which is used to solve nonlinear equation. We first will discuss its working rule or algorithm. A nonlinear function f of x is equals to 0 is given. Find 2 points A and B such that f of A and f of B have opposite signs. That's if f of A is less than 0, then f of B should be greater than 0. Then the first approximate root is given by x1 is equals to a plus b divided by 2. That's average of the 2 points A and B. Then find value of the function and determine its sign. The next iteration will depend on the sign of f of x1. If f of x1 is less than 0, then the second iteration or the second approximate root will be x2 is equals to x1 plus b divided by 2. A will be replaced by x1. And in the second case, if f of x1 is positive, then the second approximate root will be x2 is equals to a plus x1 divided by 2. That is, x1 will be replaced by b will be replaced by x1. And we find value of the function x2 and so on. Now we solve an example using the method. Find a root of f of x is equals to x cubed minus 4x minus 9 up to 4 decimal places using bisection method. Let's see its solution. First of all, we have to find 2 points A and B such that value of the function changes on these points. So we start from 0, f of 0 is minus 9, which is a negative value. We put another value, 1 at 1. F of 1 is the value of the function is minus 12, which is again a negative value. So we check another number. At 2, f of 2 is minus 9, which is again a negative number. So we will check another number. When we put x is equals to 3 in the given function, we get 6, which is a positive number. So our root lies between 2 2 and 3. Now, our points are 2 and 3. A is 2 and B is 3. So the first approximate root is average of these two numbers 2 and 3, which is equals to 2.5. Now we check value of the function at x1. We put 2.5 in the given function and calculate it. It is equals to minus 3.375, a negative number. So we will replace the number 2 at which the value of the function was negative. So the next root will be x2 will be equals to 2.5 plus 3 divided by 2. We calculate it. It is equals to 2.750. This is the second approximate root. Before going to find the next approximate root, we find value of the function at x2. And it is equals to 0.797. It's a positive value, so we will replace the number in the previous at which the value of the function was positive. So the next iteration will be equals to x3 is equals to 2.5 plus 2.75 divided by 2, and it is equals to 2.625. Now, before finding next iteration, we find value of the function at x3, which is 2.625, and it gives the negative values. So the next iteration will be equal to this one. Similarly, we find value of the function at x4, which is negative. So the next iteration will be 2.71875, and then in the similar way we can find sixth iteration, seventh iteration, eighth iteration, ninth iteration, and 10th iteration. And this is the 11th and 12th iteration. We can see from 11th and 12th iteration that the answers are repeating up to 3 decimal places, but the accuracy in the problem was demanded up to 4 decimal places, so we performed some another iteration to get value answer up to 4 decimal places. In order to find the desired accuracy, we move forward and do some more iterations. In the 13th iteration, value of x is 2.7065. We find value of the function at that point and then perform the next iteration, which is 14th iteration, and we get 2.7065. The value is same up to 4 decimal places, 13th and 10th iterations have similar values up to 4 decimal places, and that is the required accuracy. So we will stop here.